Welcome to the lesson on reaction equilibrium. This is part of mass transfer, which is being taught as part of the NPTEL-MOC on transport phenomena in materials. The objectives of this lesson are as follows. We would like to illustrate the equivalence of entropy maximization method and Gibbs energy minimization method at constant temperature and pressure to arrive at the reaction equilibrium condition. To write down the stoichiometric reaction from the equilibrium condition, to evaluate compositions from reaction constant at equilibrium, to use stoichiometric reaction for source term of each species in mass balance. So first we will take up the Gibbs energy minimization approach. So for this approach to be illustrated, we need an example system, and the example system we choose is a system that is comprising of three species, namely carbon dioxide, oxygen and carbon monoxide. So we assume that the system is a solution in single phase in gaseous state, that is all three gases CO2, O2 and CO are mixed in a single solution which is in the gas phase. The system consists of three species only, there is nothing else in the system, and the system consists of two types of atoms, namely carbon and oxygen. The temperature of the system is fixed and is T. The pressure of the system is also fixed and that is P total, P tot. The nomenclature that we are going to require during this derivation is as follows. The number of moles of carbon dioxide will be denoted by nCO2. Number of moles of carbon monoxide is going to be denoted by nCO. Number of moles of oxygen denoted by NO2. And the chemical potential of CO2 can be written either as G bar CO2 or mu CO2. The reason being that partial molar Gibbs energy is the same as chemical potential. Similarly, the chemical potential of carbon monoxide denoted by G bar CO or mu CO, and the chemical potential of O2 denoted by G bar O2 or mu O2. So we can now write the Gibbs energy of this solution comprising of these three species as follows. We write the Gibbs energy of solution using partial molar quantities. So we write it as follows. We take the number of moles of CO2, multiply with the chemical potential of CO2, and then sum it up with the number of moles of carbon monoxide and the chemical potential of carbon monoxide, sum it up with number of moles of oxygen multiplied by the partial molar Gibbs energy or chemical potential of oxygen. So this is how we define the Gibbs energy of a solution. We then know that because the partial molar Gibbs energy is same as chemical potential, we will then use the symbol mu to make it simpler for us to write and typeset these equations. So the two expressions that are denoted here, these two are identical. So we now state that reaction equilibrium is when the Gibbs energy of the system is at a minimum, and of course this is when the pressure and temperature are kept constant, which is true for us in this particular example. So the constraints that are to be posed are as follows. So if you look at when is the Gibbs energy of this system minimum, naturally when there is no species in this particular system, then the Gibbs energy will be 0, because we can already see that if each of these quantities are 0, then naturally then the Gibbs energy is also 0. Obviously that's a trivial solution, so we want to avoid that particular solution. So we have to impose constraints so that there is a balance of the number of atoms of each type. The reason why we say is because the species will change. Carbon dioxide will become carbon monoxide because of the reduction, and carbon monoxide will become carbon dioxide because of oxidation. And what actually remains the same is the number of carbon atoms and number of oxygen atoms. So we do impose the balance of the number of atoms of each type in this system, and because there are two types of atoms, then we need actually one constraint for each type of the atom in the system. Okay, so two constraints, one for oxygen and one for carbon. So let us look at the constraint that is imposed on the total number of oxygen atoms. The first constraint is that the total number of oxygen atoms, MO, is fixed. Okay, this quantity is fixed. During the reaction, as the species will change their nature, the number of moles of oxygen atoms is actually fixed. And because there are 2 atoms of oxygen in each molecule of CO2, and there is 1 atom of oxygen in each molecule of CO, and again there are 2 atoms of oxygen in each molecule of O2, we can then write MO is equal to 2 into number of moles of CO2 plus number of moles of CO plus 2 into number of moles of oxygen. And this should be written in an equation form, because the way we are going to pose the problem, we need it in a particular format. So we basically take the terms from the RHS to the LHS and write in an equation format, which is very common in constrained optimization problems. The constraint on the total number of carbon atoms is as follows. The number of carbon atoms MC is fixed, and there is 1 atom of carbon in each molecule of CO2, 1 atom of carbon in each molecule of CO. So therefore we can write the number of moles of carbon atoms as NCO2 plus NCO. So equation form of the constraint, again like we have done it for the oxygen, it is written in the form that is typical of constraint optimization, namely taking the quantities on the right hand side to the left hand side and writing it in the form of an equation with the right hand side as only 0. Okay, so the problem statement can now be specified as follows. Our idea is basically to minimize the Gibbs energy of this system, which is comprised of the 3 species, subject to the constraints that the number of oxygen atoms and the number of carbon atoms are remaining constant. So this is the problem statement. And we can then expand the problem statement saying that we would like to minimize the Gibbs energy of the system, which is written in this form here, and this subject to the constraints which are basically written in the form of equations. They are given here. Okay, so these are the conditions. Okay, so the way we proceed further is to use a method called Lagrange multipliers. So the 2 constraints are going to involve 1 Lagrange multiplier each, and therefore we choose the symbols to be appropriate as lambda O for the constraint that is about keeping the number of oxygen atoms constant, and lambda C, that is Lagrange multiplier for the constraint keeping the number of carbon atoms constant. So we can then compose the function, complete function, as follows. We basically take the Gibbs energy that has to be minimized, and we use the Lagrange multiplier, and then use the condition, the first constraint, and then we use the Lagrange multiplier for carbon here, and use the constraint for the carbon atoms to be constant. So this is how we compose the object function which has to be optimized subject to the 2 constraints. And what are the variables in this particular composite function? They are basically the number of moles of CO2, number of moles of CO, number of moles of O2. So which are there actually in this expression in multiple locations. So they are here, okay, and I am highlighting wherever they are present, and you can see that they are all over the equation. Okay, so all these are basically variables. And the way we basically want to minimize f subject to these 2 constraints is by evaluating the slope of f with respect to the variables and setting that to be 0. So that's how we do. Basically we write these quantities, the partial derivative of f with respect to the first variable NCO2, set it to be 0. Similarly with respect to the CO and with respect to O2. So these 3 basically are 3 conditions which will allow us to solve for the 3 variables, which are the number of moles of carbon dioxide, carbon monoxide and oxygen. Okay, so let us see how we go about. First we evaluate the variable NCO2. Okay, so we take the composite function and differentiate, and when we differentiate we basically notice wherever CO2 is there, we see that there is a quantity that is here in front of CO2, and there is a 2 here, okay, and there is a minus sign here. So what would it result is that mu CO2 minus 2 lambda O minus lambda C is equal to 0. So basically this is a condition that is coming out when we use the minimization of the composite function f with respect to the variable which is NCO2, that number of moles of carbon dioxide. Similarly we can choose the variable number of moles of carbon monoxide, and we then see that here again when we apply the condition that f has to be minimized with respect to this particular variable nco, then we see that it will involve quantities that are coming as coefficient of nco, and they are here and they are here. So which would then give us the condition as follows: mu co minus lambda o minus lambda c is equal to 0. So this is the second condition coming out of the equation that we have solved here. The third variable NO2, number of moles of oxygen, can also be then used. So we take the composite function, differentiate with respect to the number of moles of oxygen, and then we will see that it would involve the quantities that are marked here, okay, and which would actually give you a very simple form of the equation that comes out of this particular minimization of f with respect to NO2, which is basically here. Okay, so we now have for three variables three equations that have come out. So we can then solve for the Lagrange multipliers and eliminate them, so that we will arrive at a condition for the linking of the chemical potentials of the three species CO2, CO and O2. So the way we eliminate Lagrange multipliers is as follows. So we use one of these conditions and go about. So the very first condition allows us to evaluate what is lambda O, and that will give us as lambda O is equal to half of mu O2. Then we substitute that in the second condition we got, which will allow us to evaluate lambda C, and then we substitute that in the third condition. Then we get the final condition linking all the chemical potentials. So this is a very small amount of algebra only, but it has helped us in arriving at a condition that links the three chemical potentials, which means that this is a condition that has to be satisfied for the composite function f to be minimized, subject to the constraints that the number of atoms of oxygen and carbon are fixed. So the condition for reaction equilibrium can then be written as follows here. So there is a small change that we have done. We have multiplied every term with 2. The reason is that very often these conditions are written as per mole of oxygen. Okay, typically, usually we tend to write oxidation reactions or reactions involving oxygen. We write the condition with 1 mole of oxygen. Okay, and we could then also notice immediately that we did not have done all this jugglery of expressions, because we know the stoichiometric equation for the oxidation of carbon monoxide to form carbon dioxide. We already know that. However, I am actually illustrating only a methodology here, and when we have a scenario where there are a lot of species and multiple reactions, then writing down stoichiometric equations may not be easy. However, the procedure that is outlined here will usually work. We will now illustrate arriving at the reaction equilibrium condition using an alternate method, namely the entropy maximization approach. Through this, I want to also show you that we can actually take two different approaches and arrive at the same equilibrium condition. So the derivation is as follows. We combine the first and second laws of thermodynamics to write du is equal to TdS minus PdV plus sigma over all the species I, mu I, T and I. This is basically the combination of the first and second laws along with the chemical work that is actually in the summation here, for as many terms as the number of species that are there. And the entropy change for the system can then be evaluated by taking the ds term to the left hand side and then evaluating the quantities, and that we could actually see that by rearranging we get an expression that ds is equal to du by t plus pdv by t minus 1 by t sigma mu I dni. So that is the entropy change for the entire system. So now we actually expand the terms, and the way we expand is that we have one quantity that is here, which is a summation of the chemical potentials and the change in the number of moles of the species for the entire system, and there are 3 species for us. So for those 3 species, let us expand this term, and we expand it here as follows. This alone, the term in the green color alone, we are expanding by taking mu CO2 into dnCO2 plus mu CO into dnCO plus mu O2 into dnO2. So we have basically expanded the chemical work in terms of the 3 species that are there. And this has to be also kept in mind that the total number of atoms should be also constrained. Okay, so that actually will be used to evaluate the 3 terms that are shown with the blue arrows. So how do we arrive at these quantities? We need these, and we actually can arrive at these 3 quantities by using constraints on the total number of atoms. How is it done? We will see it in a moment. The constraint on the total number of oxygen atoms being constant is as follows. The number of oxygen atoms MO is fixed. Okay, and we already have this expression earlier. MO is equal to 2NCO2 plus NCO plus 2NO2, and we look at the differentiation of this, and we will see that DMO is equal to 2DNCO2 plus DNCO plus 2DNO2. That is the number of any change in the number of moles of oxygen atoms will be related to the change in the number of moles of carbon dioxide, carbon monoxide, and oxygen as follows. But MO is fixed, which means that this fellow here is 0, which will actually give us the condition which is actually a constraint coming from the oxygen atoms being constant. So the constraint is given here. The right hand side of this expression is the constraint. DNCO2 plus DNCO plus 2DNO2 is equal to 0. So that is one constraint that we have obtained. Similarly, by using the constraint on the total number of carbon atoms, we can arrive at the second equation that will give us the change of the number of moles of the 3 species. So the constraint 2 is on the number of carbon atoms, MC being fixed, and we write it as MC is equal to NCO2 plus NCO. And looking at the differentiation of this equation, we write DMC is equal to DNCO2 plus DNCO, and we know that the total number of carbon atoms is fixed, which means DMC is equal to 0, which then gives us the right hand side of this as an equation. So this is the constraint on the number of carbon atoms being fixed, which we can use. So we combine these and eliminate the variables as follows. We start off with the one of these equations and use that to write that DNCO is equal to minus DNCO2, and the second equation we use to substitute this, and from there we get DNO2 is equal to minus half of DNCO2, and this we will substitute in the expanded form of mu I dni, and when we substitute we can then simplify the expression so that there is only one variable which is the differential of the number of moles of the species. So we choose that variable to be NCO2. We can actually choose it to any of the 3 species. It's all equivalent, but we choose in this example NCO2 as a variable. So when we combine and eliminate the remaining 2 quantities, then we have the expression coming out as follows. So we can see that the term mu I dni is expanded to contain this term as common. Then you see that the coefficient is coming out to be so. So which we then use to write the entropy expression as follows. We say that this expression that we derived just now is going to be substituted into the expression for the entropy of the entire system. So when we substitute, we get the following expression. So we basically only do a very simple algebraic manipulation. This basically is substituted into this, and therefore we see that the entropy of the entire system is coming out to be as given here. ds is 1 by t du plus p by t dv minus 1 by t into a functional form connecting all 3 chemical potentials into dnCO2. Now here is the argument that we are going to use. We have the differentials which can be arbitrary, but we would like that at equilibrium the entropy of the system is going to be a maximum, which implies that the ds is going to be 0. And when do we guarantee that the ds is 0? For any arbitrary values of du, dv and dnCO2. So here we realize that it's an isolated system, so this quantity is going to be away. It's going to be 0, and it's an isolated system which also is with a rigid wall, so this quantity also is going to be 0, which means the way we can have ds as 0 is by ensuring that this coefficient has to be 0, because this is still arbitrary and quite possibly a finite number. So which means that entropy can be maximum if we summarize here saying that if it is an isolated system, du is 0 and it's having rigid boundary, so dv is 0, and therefore the only way we can have ds going to 0 is when we have this quantity going to be 0. So this quantity that we have underlined will going to be 0 because this is not necessarily 0, and this we would like to have it as 0. Okay, so that is how actually we are seeing the criterion that comes out for the entropy to be maximized, or ds has to be 0. So this condition is the condition for reaction equilibrium. Okay, and again we write this expression in a familiar form so that it's per mole of oxygen. So we just multiply and then with 2, and we see the form that is same as what we have derived earlier. So this is the reaction equilibrium condition for a system that contains the 3 species CO2, O2 and CO. So what is illustrated here is the methodology of going about. The reaction equilibrium condition itself could have been written directly from the stoichiometric equation, but that is not the point. What would we do when we have a dozen species and n number of equations or reactions possible? So this methodology will be able to provide the solutions still. Okay, so we can also look at the reaction equilibrium condition to write the stoichiometric equation if you wish. Now what more can be concluded from this particular discussion? So how can we use this reaction equilibrium condition to derive more value? That is what is going to be expressed here. So by expanding the chemical potential in terms of the activity, then we also know that activity means that it is going to be related with the composition of the species. Then we can see how it can be put to use in mass transfer, because mass transfer is about change of these compositions, and they can be related via activity to chemical potentials, which are then related to the reaction equilibrium condition. So this is the utility that we are actually going to achieve. So it's very important to notice that when we write chemical potentials for all the 3 species, we have to choose the common standard state before we express them in terms of the activities. Okay, and that's we write here. So the chemical potential of CO2 is written in as the standard chemical potential plus RT ln ACO2. So the standard chosen here must be consistent with the other 2 species also. So we write the 3 chemical potentials in terms of the 3 activities as illustrated here. Okay, once we have them written like that, then we can actually put these things into the reaction equilibrium condition. So we take the first expansion of the chemical potential that we have written and substitute that into the reaction equilibrium condition. Wherever we saw the mu CO2, then we basically substitute this particular quantity into that, and wherever we saw the mu O2, we substitute this quantity into that, and wherever we wrote the mu CO, we substitute that into the quantity here. So when we do that, we then can see that there are basically 6 terms that are on the left hand side, and we can collect them as 2 pairs of 3 terms each, and these are written here. So we have basically substituted those quantities. That's about it. And of course, when you look at the term here, the 2 here, it is going and multiplying in terms of the logarithm, and if you then were to take inside, it will go as a square. Okay, similarly here also, okay, it goes as a square. So we remember that and collect the terms, and we can then see that when we collate all the mu naughts together, they will come out to be an expression, and if we wish, we can actually create a symbol, new symbol delta G naught R with these quantities, and sometimes one is tempted to call this as standard Gibbs energy of the reaction. Normally we are supposed to use the word Gibbs energy for a phase, and this particular quantity delta GR is better referred to as standard affinity of the reaction. Okay, it's a better terminology, as also we see in the book by Robert DeHoff. And we can then see that the remaining quantities are going to be gathered together as a square CO2 by a square CO into AO2. We can create a new symbol called K, and that K is called as a reaction constant. and we can then call affinity of the reaction a new symbol delta GR and write it as delta G naught R plus RT ln K. Okay, and we can say that whenever the affinity of the reaction is 0, then that is basically the equilibrium condition. So equilibrium condition is nothing but delta GR is 0, or to say that this quantity is 0. And if this quantity is 0, you can take the K out and express in terms of delta G naught R, and we see that it should be represented here. Okay, so the reaction constant is related to the standard affinity of the reaction through an exponential function. And we know that this quantity is going to be a constant at a particular temperature, which means that this entire thing on the right hand side is going to be a constant, okay, at a particular temperature. Okay, that is the utility. So the condition of equilibrium is then written as delta GR is equal to 0, or the affinity of the reaction is 0, and it is also the same as writing K equilibrium, or reaction constant K equilibrium is exponential minus delta G naught R by RT, where delta G naught R is the standard affinity of the reaction. And at fixed temperature and total pressure, we can then also say that it is same as saying A square CO2 by A square CO into AO2 is equal to constant. Now we see the utility of writing the reaction equilibrium. We are actually seeing that there is a way to relate the activities of the species through a constant. This constant is basically coming from here. Okay, at a given temperature, the constant value is already known. And when we write the activities in terms of partial pressures, then we have a handle on how the partial pressures of the three species are going to be related at equilibrium. So we can write the activity of CO2 as a ratio of PCO2 to P total, activity of CO as PCO by P total, and activity of O2 as PO2 by P total. And using these expressions, when we substitute into the condition of equilibrium, then we see that the condition comes out as P square CO2 by P square CO into PO2 into P total is equal to K equilibrium. Now a word about this quantity. Very often in many of the books we normally do not see this term, but as you can actually see, when you substitute these, then you definitely have this term shown. Why it is actually absent is because very often we assume that the total pressure of the system is 1 atmosphere. Okay, in that situation obviously this will not appear. Okay, however, we have to notice that it has to be present because that will also balance the units. This is a unitless quantity, and therefore this also has to be unitless. However, if you drop this, then that will not be satisfied unless we have actually chosen it to be 1 atmosphere. So we can also define activities using mole fractions, and if you can write it as mole fractions, then you can actually also use the condition of equilibrium, and you can write it in terms of the mole fractions of CO2, CO and O2 as follows. Okay, and the way we apply these concepts to mass transfer as follows: we use these conditions to estimate the boundary compositions considering reaction equilibrium at the interface. So very often at the boundary we have a reaction taking place and the compositions are known on either sides, and we want to know a relationship that is connecting these two, and directly from the reaction constant available we can actually estimate the ratio of those compositions, and that's how the boundary conditions can be determined. So in mass transfer, the interface equilibrium, which is basically a reaction equilibrium, can be very useful. And we also can estimate the ratio of compositions from this condition. We can estimate the equilibrium compositions given the value of delta G naught R as a function of temperature it's available. And once the equilibrium compositions are known, then we can see whether the reaction is going to proceed in the forward or backward direction, knowing what is the current constitution of the system. And we can also predict in that sense the direction of change in the compositions. So in a way we know the direction of mass transfer in a system when we know what is the equilibrium and how far are we from the equilibrium, which way should the species change in order to reach the equilibrium. And we can actually use these also to talk about mass conservation. Okay, so for this to illustrate, we need an example, and I would take the example of the reduction of woostite by hydrogen to produce iron. And we can actually choose this to be one of the n number of reactions that are happening in the system, and we choose that the reaction is the jth reaction. Okay, I just choose the symbol J. I have reserved the symbol I for the species, so J is now used for the reaction. Okay, and there can be multiple species and multiple reactions in a system. Okay, so the reaction itself is given here in the stoichiometric form, and FeO plus H2 gives rise to Fe plus H2O. Okay, now we can actually then forget about what are these species. We can just number them as S1, S2, S3 and S4. So there is a small error here. This is S3 plus S4, and we can then look at the molecular weights of each of these species and use these numbers to essentially convert this equation into a way by which we can relate to the weights, okay, molecular weights of those species that are reacting. So what we do is that for the left hand side we use the scaling factor of the sum of the molecular weights of all the species on the left hand side. Similarly, we use the scaling factor for the right hand side as the sum of molecular weights of all the species on the right hand side. And we also use a minus sign for the left hand side, okay, for LHS minus sign, and a plus sign for RHS. Okay, so this is basically to tell RHS is basically the product and LH is basically the reactant, and that's the reason why we have this convention, which is quite helpful, as you would see in a moment from now. So the convention is to use plus sign for RHS and minus sign for the LHS. And so the equation now can become as follows: so 0.973 FeO plus 0.027 H2. That is basically essentially saying that 0.973 grams of FeO would react with 0.027 grams of H2 to give rise to 0.756 grams of iron and 0.244 grams of H2O. And this is useful because if we represent these constants as coefficients that go by the symbol kappa, then we can see that the sum of all these constants will then be 0, because what is on the left hand side is with a minus sign, what is on the right hand side with a plus sign. So when we add them up, it will go to 0. So the conservation of mass is basically ensured where we choose this, the symbols in this particular form. So the summation of all species in the jth reaction can then be expressed as follows: Kji, the Kji is summed up, and we see that we can actually write the summation in the following manner, okay, as I am highlighting here. So that actually ensures the conservation of mass as the reaction is proceeding. Okay, so the way we apply this to the mass transfer is as follows: if the jth reaction is proceeding at a particular rate given by a quantity Qj, and the units are kilograms per unit volume per unit time. Okay, so in 1 unit volume, how fast is that reaction proceeding? Okay, and this quantity Qj can be positive or negative to tell the reaction taking place in the forward or negative reverse direction. Okay, and once that is available, then we can say that the rate of creation of ith species through the jth reaction is given by a particular term that is given here. You can see here, okay, K kappa ji into Qj. So that actually gives you the rate of creation. The reason is that the kappa is actually the coefficient, and Q is basically the rate, and when we multiply, then we should get what fraction of this mass is actually created because of the species I. And let us illustrate that with this example of woostite and hydrogen reacting to form iron and H2O. We can say that the same thing we can write here. So we can write the same thing here. In this reaction, let us say the reaction is proceeding at Qj is equal to 2 kilograms per unit volume per unit time. Then it means that the iron is produced, namely this into 2, so that comes to 1.512 kg per meter cube per second, and FeO is consumed, this into 2, that comes to minus 1.946 kilograms per meter cube per second, which means that we can actually use these expressions to arrive at what rate the species are being produced, which is plus sign, and consumed, which is minus sign. So when we sum up these of all reactions, then we can say that for every reaction we should write the production or consumption of each of the species, and for the ith species due to all the reactions, then that would be a sum up of these quantities which we have seen here. So for the jth reaction, it is basically kappa ji into qj, and then we sum up for all the reactions. J goes from 1 to r. There are r number of reactions, and therefore the total creation or appearance of the ith species given by the quantity q is then expressed in this form. Now this is going to be useful because this becomes the generation term during the governing equation for mass transfer, and the generation is coming because of reactions. Okay, and this entire discussion is borrowed from two books, the book by Robert Dehoff and the book by De Groot and Mazur. Both these books are very deep in these respective subjects, and if you are interested in more thermodynamic aspects of the reactions or reaction equilibria, etc., then I encourage you to go to these books for more information.